So that's why it's here. You see, but when fault occur within the zone, yeah, then this current here and current here cannot be equal. There are going to be a change in current and also what, a change of voltage because what fault has occurred because our initial voltage or initial current will not change, is it? You know what we know.
Yes, sir.
Uh-huh. So that is what I'm explaining on the right up here now, here, where my person is now. That is what I'm explaining here. That this and this are not equal because there's a change in current. And our change cannot be the same. Our current here and current here cannot be the same. They might have a different value. So therefore, this cannot be equal to that. That this cannot be equal to this. Hmm? Mm-hmm. Okay. So in that case, I told you about in this case that for what for the relate to operate here that our operating core must be higher than what the resistant core, which I'm going to explain better now. In the next slide, it explains what's there. So that is it. But know that our current here and here are not the same again because current fault has now occurred. Okay. Now this is voltage balancing. So also in voltage balancing, it also follow the same thing because in the external fault that the current that what the voltage that what in the external fault that the voltage is what is equal in the external fault. But in our what in our internal is the reverse is the case. Our internal that the voltage is not equal. That in voltage balancing differential relay. But the other one, the first one we explain it is current was balancing differential relay. So the different line is the opposite of these. That's the voltage balancing and current balancing. They are opposite. Is that okay? So what happened in the internal in the current balancing is what happened is what in the external is what in the voltage balancing. And what happened in the internal balancing of the voltage balancing is what happened now in that one. So it's just vice versa. That's what the difference between both of them. Okay. Now we are trying now to explain here where the operating that what like these are what our differential relay operating. Now this our what this our operation here. This our what restraint. This our restraint. Now in this slide we are told that this for this to operate then it must be greater than what this restraint. That is just what I'm trying to show that. So I'm trying to emphasize it more and more because it is very, very important. So you have to know it very, very well. Now I might jump to this that you're going to tell me here now. That in our operation zone and in our restraint zone. Now our that operation zone that I operation is equal to what? The I S1 plus IS2. That's our operate. Then our restraint will be IS1 plus IS2 over 2 or times half because of our restraint. So we are plotting a graph of operation against what? Restraint in this case. So our restraint value will fall here, will fall this zone. And our operation value will now occur this zone. Now, what I'm saying here is that our IS1 minus IS2 times the operation zone. Oh, this guy, look at this thing. Like this operation now, will be now that this operation current or over current will be equals to IS1 plus IS2 all over 2 times our restraint current. Then our IS1 minus IS2 times our operating cost will be equals to 1s1 plus 1s2 times k times our operating cost. Then I told you that this k is can be gotten by or can be obtained by or our strength coil all over our operating cost. So on the look at what I put it here. So it's very important. This formula is very, very important. Because sometimes no one will tell you in the exam or in your self, you're supposed to live by yourself that the strength coil all over the strength operation will be is equal to K. So that's how we get our K. So when we call it K, so that's how you get it. Is that okay? Now when S1 is greater than and what is greater than what is greater than S1 and S1 plus S2 times K plus this. So then this is what will happen. Then if we also put this into that, we're going to have that. And then our S1 now can be gotten by can be gotten with this. So that's how you can get your S1. And your S1 must be greater than this. But this value here. If not, the operation coil will not operate in this case. So our S1 must be greater than this. Okay, which means your S1 here must be greater than what this S2. Is that okay? If not, that will be disaster. Okay. So I'm going now. We're not going to generator precise. Now we're only considering generator here in 3 phases. So you will notice this topology. So I'm going to explain here again. I will discuss about this. So let me just go so we can discuss about example. So you can understand it here quick. Okay. Now this topology is when.
So we this right up now.
Huh? You say?
This right up that you are flipping over.
I've explained all those things. So you are not wasting our time there. As I'm talking, I know what I'm talking. I'm explaining, so we don't need to go back again. So I have to not to waste time. Now I'm just trying to show you here when for two-phase fault in this case in the generator like two-phase fault. So just the topology here, and this is our balancing our display coil, and this is our operating coil. So I've explained that. So it's not new to you again. CT is another rest. You know about this ones now. If fault occurs between any two phase phase B. So we're going ahead. This one I've explained it. I want to go to calculation. That's my interest, so you understand it better. Okay. Now I want us to take this example so that you understand it better. Now, in this figure here, look at this figure here. A fault has occurred in the appliance or in the equipment. What has occurred? Let's read the question. That figure 2 shows a biased percentage relay applied for the protection. And shall let me just go straight. Now, this is the relay now. Now they say fault has occurred in this winding. Fault has occurred. And now they are giving the what the CT ratio. Our CT ratio, our CT1 is 500 is to 5. Our CT2 is 500 is to 5. And now they are saying that the current flowing through the CT1 is what? 420 plus JO amps. And the current flowing in the CT2 is what? 400 plus JO. That's the current. And now, these are the same core. These are the same core. These are operating core. They are not asking. Will this relay operate or not? That is the question here. That is you can read by yourself. Okay, let me give you 1 minute to read the question. So that when we are going, you know it. us not to do something. Are you with me? I hope
So
people
I'm
have
going
their
to the
paper.
solving.
Huh? Understand the question first. We are coming to the solving. You understand the question? I don't want to read it because it's there in the slide. I hope people have paper to be writing because I see that you guys are not writing anything. I can see you guys here. You guys are not writing anything. So it's like we're not in a ball. Sometimes it's not what will be proved as can solve. So when we are talking, things will become repetitive. So you people should be having book where you're writing. You can just stand like executive. Buhari, reporting. You people should none of you have book. It's not very. I'm seeing you guys. You have read the question now. That's fine. So the first one is above this. That one, the question is now the question A. That will the relay operate or not? That's the first question. Will the relay operate or not? Then two is will the relay operate at the given value first current in A above MFI the generator was carrying no load, and C then draw what the diagram of the this thing. Who is coming again? Now people are coming now. This guy Tony. Okay, so now let's go to our first question now. Now the question is now will this score will this this will this operate? Will this operate? Now we're going to see. Now this is the solution now. Now our ST1 that is this year we are having our current to be 420 plus 0J that is it. So we are going to only take what the real part of it, and we're going to the imaginary part in this case, and then times the ratio of the TC1, and when we calculate this, it's going to give us what 4.2 amps. Are you hearing? Are you understanding it?
No.
No. Now, fault under load. This is fault under load. Now we're saying that this that S1, you are making noise now, that this current here, that the current flow in this place and the current flowing here, look at the current flowing here, that this current here, that was not taking this times that times the CT1. These are CT1 here. And they are giving us the ratio of it, that is 500 is to 5. That is the ratio. So that is it, that is the ratio. So this times this will give us what? That. Is that okay? And again, for that, again, too, for this, the current through here, that this times that will give us that. So the current here, who is making that noise?
We should stop talking now. Eh?
So this current here, the current here now is a 4.2 amps. Then the current here now is 4 amps. Now, I want to see something. Now, if you now minus this, this minus that, we want to know the difference between this and this. Because when first has occurred, now the difference between both of them now is what? 0.2. That is the difference between the current here of the city current and the city current 2 is 0.2 amps. That is different. Now, the same code, average current is what? Is now, if you go to our map, our this and that is here, you go here, this formula, where is it? Yeah, we are now we have the current. That's what I'm talking. So you use the formula. Yeah, that's what the difference between the operating current is now is that the difference between this and that. That's operating. Now the restraint current. Now we have gotten our operating current to be 0.2 amps. Now our restraint current is what this will give us what 4.1. So you can see that here our what our restraint current is high. So we are going. You want to know that it is for call. Then go to relay. But the relay is going to operate at this point. But we have current. Like if you go, what is that?
Thank you. Thank you.
Who's making that noise? Who's making that noise? So I will not let's start on that again. It's over here. So now in our restraint, they say it's 10%.
No condition.
For this allegation.
Okay.
Yeah, try away. Okay, yeah. Now we are told that now we have that this is the 10%. That the same core is 10%. So now, and this operating core must be greater than or equal to that. So
Hello, please, sir, can you make it a bit bolder? Just like to be a bit bolder so we can see the character, please.
It's good already. It's good. Then you can make it aside. I put in the maximum. That's the highest maximum. So now you can see that this operation here, that this value here must be greater than this value or equal to this value before it operates. So if this value is higher than this value, then our needle will not operate. And you can see in this case now, the value that is what 0.41. So in this case, this value here is not at this value, then the relay will not operate. You put on as you go. Do you understand that?
No, sir.
As you go, this is more mathematics.
Why
But you understand the question. That's the most important thing. I like you to read the question. Now, in the question, the first stage, the first part of this question is they're asking us, will this relay operate on this data? So I want to see whether this relay will operate on the data they have given us. They are told that the CT1, that the ratio of is given as ratio because it's a transformer, that the ratio is given as 500 is to 5. And the CT2 is given as 500 is to what? 5. That is the value. It's a transformer. And now they say the current flowing here, when fault has occurred, is 420 plus JOR. And now the current flowing here, when fault has occurred, is what? 400 plus J0 amps. Now they're not asking us, will this relay operate or not? I told you guys, this relay can only operate when the value here is greater than the value here. And that's what we're doing here. Right. Want to know the value here? You see it now. Want to know the value here?
What do you mean the value here? Is it the operating?
Look at the value. Look at this value. Look at the calculation. The value. Look at it.
Okay.
Look at this here. That's what I'm doing. That's the calculation we're doing here. So we're not calculating what the current here and the current here. And now the current here, the current flowing here, we are saying that is what? This times that. This value will give us what? This current. And this times that will give us this value. And these two values, that is it. And now we're saying that now this value here we have now, which is this value now, minus the value we have here, which is this value. And that what we do here is what 0.2 amps. So which means this core, the current flow in this coil now is 0.2 amps. So we have got our value now of the operating core, the current flowing through the operating core. It is value. But we want to understand that now, that this value, that this thing can operate only when this value here, when this value is greater than this value here. If it's not greater, then it will not operate. So this value must be greater than this value for this rate to operate. But this is a restraint value and this is operating value. And that's what we're doing here. That's what we're going to do here. Now, when I come to restraint, we are finished now our operating. We know our operating current to be 0.2 amps. Now, our restraint here, this restraint, we want to know the value here. In our relay. Now, we are going to that. Now, our restraint current would be this plus that, all over that this plus this, all over 2. And now plus that, this plus this, that this plus this, all over 2, we give us 4.1 amps. Now, in this case, that will tell you that this will not operate because now the current flowing here is greater than this. But we want to investigate more to see what's going to happen more. Because they told us that this value have 10% in our system. So we must incorporate it. So 10% of this core times this value here, we give up 0.41, which is still greater than this value.
Yes.
So which means since this is greater than this value, then this will not operate. Because this must be greater than this value here. And that is why this relay will not operate on this condition. You understand it now?
Yes, sir.
Differential relay operates. So if you don't understand it now, tell me it's simple. Logic.
We'll go back to it, sir, later.
Huh?
We'll go back to it.
Now the P now part of it. Out of time, run out of time. You should tell me when this is disturbing. And the generator now under no load. Now there's no load. Now the value, the first current is same as what in the current one, in the question 1, which means we can just go straight that this minus that is here minus that is not equal to 20. So which means now there's no load. So look at the current here is also equal also as what the fourth current because there's no load. Is that okay? Then which means now our
Sir.
yeah.
Yes, sir. I discovered that the values, this 420, it has an angle. But you are using only the real part, the 420.
The 420,
even the 400.
It's not 0 they give you there.
Okay.
Does it have any value there?
I think it's 0. I saw. I think it's 0. I saw.
So 0. When you see 0, what does it mean?
Okay, sir. Go ahead, sir.
So now, in this case now, we have 20 times that. We give out this current. Because the current they are the same. Now, which means that current flow to the operating coil. So which means now this current is flowing here. So now we can see that our I here is 0 because no current is going on that side because there's no loop. So current is not passing through that way. So our S1 here is equal to what? Our S2. So our S1 is equal to our F2, our first current.
I'm in class.
So this is what? 0.2.
My teacher.
So in that case,
My teacher.
our operating current is now
Yeah, we'll log you out.
IS1 minus IS2, which is what? 0.2 minus 0 will give us what? 0.2. Now look at it here. The current here is 0. Look at it. So it's 0.2. Then, our current, our same current, over 2 equals 0.1, which is less. So in this case, it's telling you that the operating curve will break because already this is higher than this. So since operating curve, which is this, is greater than what the same curve. Therefore, the relay will operate because this value is not at this value. So the relay here now will operate. Is that okay? Any question? Eh?
Left for this and stop this COVID-19 so we can come back to class.
But here is not hard now. What are you talking? Here is just simple. Now, we cannot plot this from we're not going to plot this one is operate against what? Restraint. Like in the question here too, we're going to plot operate against what? Restraint. So our restraint is what in the horizontal. That's the thought question. That I should plot the diagram. Look at it. That's the thought question. On the same diagram. They have locked me out. I see me. Characteristics want to plot. Then we're saying in the same diagram we should plot the what? The operating side and the restraint side. So we're going to do values. So we're plotting that. So if you have your pen and paper there now, you can just so that in the exam you won't complain. So if you have your pen and paper, right now this y that's 0.4, 0.2 amp y, then 0.41 z. Write it. Are you writing it? That's right. You will not tell me. You are not coming with pen in this class. That's what I'm saying.
Will happen. 0.2.
0.2 is which for y. Then 0.41 amps for x axis. So we're having that is the point. That is the point. Okay? Then the second point, we have the second point. The second point now is y is 0.2 and z is 0.1. Is that okay?
Z.
You have it now.
No.
Oh, look at it now. Look at it here. We are not trying to plot these 2 points. That's what we are plotting now. We want to plot these 2 points.
0.2.
Now in your y-axis, we're going to have 0.2. In your x-axis, we're going to have 0.1.
Okay.
That's what we do. We have 2 points now, isn't it? So now we can see that we are not great now our y-axis. Our y-axis will have the highest number as what? As 0.2. You can start for 0.1, 0.2, 0.3, 0.4, 0.5. And the y-axis now is our what? Our operation. Then our x-axis, we have the least one as what? 0.1. So we can start what? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Okay. Isn't it? So in our point 1, in our first in the part A of the question, we have the current, the operation is what? Operating is what? 0.2. That is, we are going to put our 0.2. And now our restraint is what? 0.41. So you're not calling a question, you draw your line from your graph. You not plotting the 2 points. We are plotting 2 points now. Anyway, they meet. 0.1 is about this point. Then you now mark it. Then our point 2 is what? Our operating is also 2. Then our 1 is x. Is x. Is x. Then where they meet, we drop 1 x. Y. So this what they mean. Then you now draw a parallel line from your origin to show your what? Your operating region and restraint region. So if you take this line now, you can see that now our operating current appear on the upper side of the graph above this line. Then you can see that what our restraint current fall below this line. So that's what the plot here. Any question?
Okay, we choose the best points on the graph to plot our straight line. Now we have 2 points. We have 2 points at 0.2 and 0.1 on the x-axis and 0.2 and 0.4 on the x-axis and y-axis. How do we draw our line to shade off the region?
I will explain now that you take from the origin, just a straight line. And if you do in your regression, if you do statistics, huh?
Sometime ago.
I'm asking now, ask me, what you do?
Yes, I did statistics, but I did statistics.
This was a graph of when you are doing regression, when you plot your scattered distance, I think you just go from origin.
Yes, sir.
Then you want to follow the region, you take the region. And what we're trying to establish here is now we're trying to establishing the operating region and restraint region. And what we see here is that the point of the operating values will fall at the operating region, and the point for the restraint region will fall at the restraint region. Now, if you now take your line from the origin, and if your restraint now fall at the operating region, which means they're wrong. Are you hearing me now?
I can hear you.
So it must not, the line must not fall, what you said, it must fall in the line. Cool. So you didn't do mathematics where it is not all your points must fall within from the origin, where you're taking the origin. When you are doing a straight line graph, it is not all your points will fall there. So when I fall there, you take it. The one that fall outside, take it. Huh?
Okay. I'm just looking at the graph on the slide.
The graph should not. This primary 6 now. Don't look at the graph. This you don't have time here. This is 7 primary 6. You're talking about here. Talking about here.
But it's a very master's class now.
This was go and read your scatter diagram. Go and read your regressions, and go and read your this thing. What is it called? Interpolations. So go and do those. Go and do your statistics and come back. So if you do your mathematics well, go ahead with your question.
The K is supposed to be 10%. You didn't use it.
Huh?
But the K is
Is it?
10%. The K is supposed to be 10%. You didn't use it here. You use it on the other side where you multiply the restraining current by 10%.
Then what is the fault there? Why? Because here now we are getting our value here already. Now in this case, you see that our operation value is 0.2, and our restraint value is 0.1. At this point, the relay will operate. It will operate immediately. But in that case, we still investigate down to see how it can operate. We deploy it. It doesn't operate. So are you going to clear that? And this case, in this part B, there's no operator already. Without wasting time. But in that part A, we are trying to investigate why the rate is not operating. And we go down more. We see that we use all the parameters. within the restraint region, and yeah, it does not operate, which means we can conclude this cannot operate. But in this case, in part B, we see that the operating value is 0.2 and the same value is 0.1, and the relay has operated already. So what are you going to do? And it's not reading alarm for you for reply. So what are you going to do again? Eh? Are you okay now? This technical thing, so you more have to do technically, not with the literal mind or literal this thing. At this point, we are talking technical things. Huh?
You technically also.
Huh?
You also have to follow it technically, sir.
Technically, that is it. So you should not bring my on my one idea here, or on the graduate idea. You have to reason it. You have to reason it. Use technically. Use technical idea. So all the questions I'll be giving are not okay. I'm going to give you assignment today. So the people I'm I have let me just see the name I have here. We're going to send Eze gave me 12 names. So we're going to send I'm going to send the assignment through there. And the assignment, you are going to pass it on the 19th. On the 19th of this month. So it's going to be part of the assessment. So you must see it in your email. I think Eze gave me he gave me wisdom, listen of Amadi, Michelle, Oji, distance relays come in place. And that's why we have lots of feed. So you can see the diagram for rotor. What we did was for stator. Okay. Now this one now is for rotor. So you can see that we have our CT and our VT or our P or VT or PT here. So this can be what in form of a reactor. You understand? So and this can be also as a reactor. So in our distance relay or our impedance relay, there must be the CT and the VT in place for it to work. If not, it's not going to work. Is that okay? Is that okay? So in that case, and in our rotor, because rotor is always connected to the feed, it's at the feed down, and that's why we are going to have some DC voltages around it. And now sometimes we can offset this DC voltage, and later maybe in this course I'm going to show you how we can offset this DC voltage, because sometimes it can bring some negative values, or it can bring some harmonics in the system. So that we have to get rid of these DC values from the rotor, so that now to free from a harmonics problem. Is that okay? So we're going to show that. So in the rotor, we also have the abnormal condition, the overvoltage, the overcurrent, undercurrent, overexcitation, reverse power, and out of step and unbalanced current. Although we will not go through all of them, we will just as we did in that stator, we might just go one because of time. Then after that, we're going to go into a kind of to use the asymmetrical component to solve the fault currents, or to protect the motor or the generator against fault. So we're going to see it maybe tomorrow if time permits. They say our listeners stop clearing. So in fact, we'll see it tomorrow then. What's the time? To 4.
12 minutes to 4.
We'll see tomorrow. Kingsley.
What time?
Huh?
What time?
12.
Sir, excuse me, sir. Sir, can
Talking?
you use, yeah, it's wisdom, Alale. Can you use the same ID and the same password so that people may not be...
No. because you see, the problem was the one I booked before was not appearing, so that is why. So I want to give one.
No, because like what I'm saying is the like prop own, we are using the same ID and the same password. So if it will be postal like that, people might not be confused also.
Yeah, time and date and the password.
Okay.
So
Okay.
if you use single ID and single password, everybody will know that okay, this is the time.
Wait now, because it's recurring. I didn't pick a recurring. Like you and Pro, people have it the same time, the same day.
What?
Yes.
No, what I'm saying is this.
And
No,
I know,
like
wait. When people have Pro, which day is that? Which day?
Like today now we're having prop by 4.
By 4. So next
Yes,
week also
today.
people have at 4.
Okay, we are having.
No,
It doesn't work like that. Anytime.
it doesn't work like that.
Okay, I'm going to generate it by myself. So okay, I'm going to do it myself. So I'm going to generate the same password. Is that okay?
Yes, sir.
Is that
And
okay?
the same ID.
And say that's okay.
Yes, sir.
Like this one can still work, sir.
So which one people prefer? Is this one?
This one,
one,
okay.
yes.
This one.
Great.
Because everybody has known this one.
This one is fine.